So what's MSA and why it's needed? MSA, again, I'm going to talk about this in more detail a little bit later on, but MSA warrants organizations to evaluate their quality measurement system, which in return provide better product quality. And I'll explain that to you how that actually happens. And the reason I put this together on this slide here, we're kind of comparing where MSA fits in the quality core tools. As you can see here, it's the one of the 5 core tools that we use in automotive. And again, it's also used in aerospace. So what's the linkage between APQP and the quality? Again, whatever we do, either product or service, everything we do is for customer satisfaction. And that's our ultimate goal. In order for us to reach that goal, we definitely need to have, again, robust designs or services, producible products or repeatable services, capable processes, timely production and on-time delivery. If we don't do these in the order of a product lifecycle or a service lifecycle, you will always get complaints from our customers, which means it's going to drive customer insatisfaction. Then you need to come up with corrective actions and potentially a loss of a customer, right? Depending on the severity of the issue. So because of that, I wanted to make sure that everybody understands the linkage here and then talk about more in the MSA. So what is MSA? The measurement system analysis, MSA, is a set of entities used in the combination to take a measurement of products or sometimes product key characteristics or key features or process key parameters. And some of these entities may include actually the gauges, the standards, the operations, the software, the personnel, environment, and the methods that personnels are using, and so on and so forth. But the purpose of MSA is to quantify the variation, also known as the error. And that variation, of course, we're not talking about the product variation or process variation. Here we're specifically talking about the variation introduced by the measurement system. So let me kind of define some of these terms that we're going to be using throughout the this webinar. Starts with measurement. So what is a measurement? It is defined as the assignment of numbers or values to material things to represent the relations among them with respect to particular properties. Then the gauge is any device used to obtain that measurement. The measurement system then is the collection of instruments or gauges, standards, operations, methods, fixtures, software, personnel, environment, assumptions used to quantify a unit of measure. The standard then is the accepted basis for comparison. It's also known as the criteria for acceptance, known value with stated limits of uncertainty, accepted as a true value, or in some cases, it may be called as a reference value. So a standard should be an operational definition. So what does that mean? A definition which will yield the same results when applied by the supplier or customer with the same meaning yesterday, today, and tomorrow. So now that we know the high-level terms of measurement system analysis, let's look at some of the basic equipment-related terms. And it starts with discrimination, readability, resolution. And for that, we need to define the LAS, which is the smallest readable unit, measurement resolution, scale limit, or detection limit. An inherent property fixed by design, also a smallest scale unit of a measurement or output for an instrument. The effective resolution is the sensitivity of a measurement system to process variation for a particular application. The reference value is the accepted value of an artifact and requires an operational definitions. The true value is the actual value of an artifact, also known as the unknown and unknowable. So let's look at this, the set of curves here. This normal distribution curve, if you look at, there are multiple curves, right? The way we're going to interpret this is that this the dotted line curve is representing the actual process variation. So think about it, you actually measured parts, and that's the curve that you got out of your process variation. The small ones right here, there's one on the left and there's one on the right tail. They are representing the production gauge variation. So when you have the process variation plus the gauge variation, the sum of those will give us this red observed process variation. So depending on where the specs are in this curve, these additional production gauge variations may actually affect the decision of the operator to decide if this part is good or bad, right? So because of that, the amount of this variation due to the gauge is critical. So let's keep that in mind. Some of the properties of MSA, certain fundamental properties that define a good measurement system, and these are like adequate discrimination and the sensitivity. So what does that mean? It's the increments of measure should be small relative to the process variation or specs. The commonly known rule of 10 or 10-to-1 rule states that the instrument discrimination should divide the tolerance into 10 parts or more. So that's actually, because of that, when we do the gauge studies, there is a discrimination rate that we actually get from the statistical analysis, and we expect that to be higher than 10. If it is not, then we need to work on the gauge, because we don't accept a gauge with less than 10 discrimination rate. The measurement system also ought to be in statistical control. So under repeatable conditions, the variation in the measurement system is due to common causes only and not due to special causes. This can be referred to as statistical stability and is best evaluated by graphical methods. For product control, variability of the measurement system must be small compared to the specification limits. On the other hand, for process control, the variability of the measurement system need to demonstrate the effective resolution and be small compared to manufacturing process variation. So we already talked about the, I mentioned the sources of variation as common or special cause. The measurement system impacted by both random and the systemic sources of variation. And these sources of variations are due to common cause and special cause. In order to control the measurement system variation, we need to identify the potential sources of variation and eliminate whenever possible, or monitor these sources of variation. We actually use an acronym called SWIPE, SWIPE, and this is used to represent the 6 essential elements of a generalized measurement system to assure the attainment of required objectives. SWIPE stands for standard, workpiece, instrument, person, and procedure, followed by environment. So we're going to actually, on the next slide, I'm going to be displaying the cause and effect diagram showing some of the potential sources of variation. So if you look at that, so here is, for those who have never seen a cause and effect diagram, this is what that is. Here's your measurement system analysis of variability. And again, instrument, the workpiece, the swipe, right? The standard, environment, and the person. So we need to look at all these options to see where else we could actually add variation to our measurement system analysis, considering those 5 main areas of variation. So looking at the workpiece, if you look at that, it says hidden geometry could be a variation, operational definition, adequate datums, supporting features, elastic properties, and so on and so forth. When you go to the environment, it talks about the lights and vibration, the air pollution. Again, everything we're going to talk about later on, the common mistakes with measurement system analysis, and some of those, actually one of those common mistakes are that, the measurements we are conducting them in the real, manufacturing environment. But when we do the MSAs, and I haven't heard from anybody that they're actually doing it on the manufacturing environment. They tend to be conducted in the lab environment. So the environment not necessarily the same at that point. So when we do MSA, there are 2 different types of MSA that we do. One is called the attribute agreement analysis, or attribute gauge R&R. That's for the discrete data. And when we do that, we look at the repeatability, accuracy, reproducibility, and team accuracy. And so the attribute agreement analysis, or the MSA with attribute agreement, So in this case, the MSA that is used to assess the repeatability and accuracy of individual inspectors, as well as the reproducibility and the overall accuracy of the group of inspectors. Repeatability here is obtaining the same results when measuring parts multiple times. Accuracy, obtaining repeatable and correct results as compared to the true value or the reference value. Reproducibility is obtaining the same results across all inspectors. And the team accuracy is obtaining repeatable and correct results across all inspectors. The gauge R&R, this is for continuous data. It's a type of measurement system analysis that is used to assess the precision of the measurement system. It is used to determine how much variation is present in a measurement system by combining the equipment variation, which is the repeatability, with the operator variation, that is the reproducibility. The most commonly used MSA method is the gauge R&R. And in a good measurement system, part-to-part differences are the largest variation. I'm going to show you an example of that later on. Here is the criteria the gauge R&R acceptance criteria. There are 4 different indicators we can look at for gauge R&R, but the most commonly used one is the second one here. It's called the % study variation. And as you can see here, it says the measurement system standard deviation as a percentage of total process standard deviation. So the green, which means acceptable, is that we have to have less than 10% of variation that's due to the measurement system. If it's between 11 and 30%, we call that marginal or yellow zone. What does that mean is that it depends on what you're measuring and the agreement between you and your customer, technically. If your customer doesn't approve it, then you need to make improvement on your gauge or measurement system to bring that variation down to less than 10%. If you see a variation that is greater than 30%, most likely that is going to be rejected. Here's an example. As I was pointing out, we want to see the part-to-part variation that's largest, and then the gauge R&R we want to see, and this right here is represent repeatability and the reproducibility. As you remember, I mentioned repeatability is due to the equipment itself. Reproducibility is the variation due to among across the inspectors. And this is the total of these two, technically. So we're saying that this example, the gauge R&R value is about 30%, maybe a little bit less than 30%. The number of distinct categories within the process data that the measurement system can discriminate. As I was saying before, there's a rule of thumb of 10 to 10, not thumb. So you want actually when you measure 10 different parts, and your measurement system could discern 4 distinct categories. This means that some of those 10 parts are not different enough to be discerned as being different by your measurement system. So a value of 5 or more denotes an acceptable measurement system, even though earlier I said 10 based on the rule of 10 rule. But I think the 5 in Minitab, so if you were to use a Minitab to analyze or conduct your measurement system analysis, the Minitab will actually give you the not only the percent study variation, but also the distinct categories. And if you see that it's 5 or more, you can accept the gauge, the measurement system. The percent study variation, as we talked about already, is the ability of a gauge to differentiate one part from another. So here are a couple of examples. This one over here, as you can see, the part measurements are like overlapping. So there's no way for our measurement system to differentiate from part to part. And on the other hand, on this one, when you don't have an overlapping confidence interval, which means our parts are so different from one another. So if our gauge can actually differentiate that, that defines the health of our measurement system. So when you are developing or let's say you don't know what to do, what kind of measurement system to develop for your processes or measuring your products, there is a checklist that you could use, and I try to do my best to provide that list here. So you should start with what is to be measured, and who will use the who will use the process. For what purpose will be the results of the, before I say who will use the process, I need to also point out, so when you decide what is to be measured, then you need to also know for what purpose will the results or the output of the measurement process be used. Then who will use the process? Is the training required? Have the sources of variation been identified? Has an FMEA, failure mode and effects analysis, been developed for the measurement system? Flexible versus dedicated measurement systems? Contact versus non-contact environment is important or not? Measurement and location points, fixture method, part orientation, part preparation, automated versus manual system, destructive versus non-destructive measurement, potential measurement range, effective resolution, sensitivity. So these are, again, at a minimum, some of those criteria you need to consider, and you can again use this as a checklist when you're actually determining your measurement system. You can also look at your measurement system build issues, equipment or standard instrument. So in this case, you need to define the sources of variation identified in the system design, calibration and control system, input requirements, output requirements, of course, the cost, preventive maintenance, serviceability, ergonomics, safety considerations, storage and the location, measurement cycle time. Will there be any disruption to process flow, like lot integrity to capture, measure, and return the part? Material handling, environmental issues. Are there any special reliability requirements or considerations? User instructions, spare parts, documentation, calibration, storage, and error mistake proofing. Again, you need to consider all these for your build issues. As I was pointing out, when we conduct the measurement system analysis, we do make some common mistakes. And it starts with actually MSA are being conducted in the lab or in the conference rooms as compared to, again, in their real manufacturing environment. Introducing bias error, in other words, time of day, non-random order, appraisers, not independent, etc. Allowing extra time for measurements and review. If you think about it, when we're out on the shop floor and we're measuring part, if you are the operator, you have a minute to complete your whole cycle, right? Building it and measuring it. But when we do the MSAs, nobody usually cares about how long it takes for the appraiser to measure that part. Misinterpreting the results, acceptance versus improvement, for example, not involving all appraisers. So you have 3 shift operations and you're only doing the MSA using first shift operators. So that's a big mistake actually. Using own expert whose assessment differs from that of the client's experts. So if you think about it, if you're measuring something and then you send that part to your customer, and the customer actually measures that, and you two are using different methods, then most likely you're going to get different results. And what's going to end up happening is that your parts are going to be rejected, right? Because customers is going to think that they're doing everything right, so you are the blame. So for that reason, part of the measurement system analysis, we must communicate with our supplier, our customers. And if you're the customers, our suppliers, to make sure you use the same method, the same equipment, the same technique, the same, and your people are trained well and the same environment, right? So we need to be careful with that. Doing MSA for a part specific study, but applying it to a family of parts or vice versa. So I know when we talked about the PFEMAs and the DFEMAs, we actually conducted on a part, and then we use it actually for families of parts that are very similar, and we only capture the differences. But when you come to the MSA, it's different. So we need to make sure that we actually do it on all parts, not just specific one. Not involving all appraisers, as I was saying before, and types of gauges. So if the appraisers are using different types of gauges, right? You can't just do it on one type and then assume that all the gauges are good. So you need to, again, make sure that the MSA is conducted on all types of gauges. The types of variable gauge R&Rs in Minitab. So I'm going to walk you through some examples how it's done. And of course, I'm not going to spend too much time on how it's done. But one thing I want to point out here is that the variable gauge study can be performed using a number of different techniques, but the 2 acceptable techniques that we use, or the methods we use, are called average and range method and the ANOVA method. The results are very similar for both, but the ANOVA method is preferred because it measures the operator to part interaction gauge error, whereas the average and range methods does not include this variation. The ANOVA approach is preferred because of also its flexibility. So if the user has access to an appropriate computer program, if not, the X-Bar and R approach is appropriate and can be done manually or via a computer program. So operating flow of an R&R study by variable. So first of all, you're going to select 10 to 20 parts and number them. Calibrate the tool. Make sure or be confident that is currently and properly calibrated. Usually the tools have stickers on it, shows the calibration date. So you need to make sure that calibration is not expired. The first operator has to measure all parts in random order. Then the subsequent operators have to measure all parts in random order. Go on until all operators have measured all parts for the first time. Repeat steps 3 through 5 as many times as requested by the plan. And what that means is it's called actual replication. So We usually do 2 to 3. In the process, that the data to produce statistical outcomes, Gage R&R and the graphs. And you need to finally analyze the results and define, if requested, all necessary countermeasures. So what does that mean? You may need to have a new tool, training the operators, improvement of measurements, instructions. So again, at the end of your study results, if it's not acceptable, if the variation is less than 10%, if the variation is not less than 10%, some kind of corrective action is needed to reduce that to acceptable level. And that's why I just listed here, maybe you need a new tool, or you need to train your operators, or improve the measurement instructions, and so on and so forth. Here is how you do this using the X-Bar R method and the ANOVA. So if you look at here in Minitab, you click on the quality tools from their Gage study. Before we conduct this study, right, you need to create a plan. So this is showing you, okay, you need to click on create the Gage R&R study worksheet. So when you do that, you're going to get to a screen where you're going to define your parts. Again, if you are only numbering your parts 1 through 10, or if you go alphabetical order like A, B, C, D, you can just type them up here. And then the it says number of parts 10, number of operators 3. So 3 operators, and you can actually type in the operator's name. So you will know when actually plan is printed out, you will know exactly. So you can call John, you're doing this. Serhat, you're doing this, and so on and so forth, instead of calling operator 1, 2, 3. And down here, it says replicates of 3. So what does that mean is that we're going to repeat same operator measuring 10 parts 3 different times. So 3 times 3 operators times 10. So we're going to actually collect 90 data points. So when it's done, here is a section of the, if you look at here, it says run order 10 is the part 4 to be measured by operator 1, and when he or she measures that, that's the result that we get. So this is not showing exactly the plan that is created here, but at the end, that's what's going to happen, and you're going to add this column, what they're going to be measuring. And you may actually have multiple measurements here, so you just need to keep adding those. So if the operator is measuring part 1 for measurement 1, measurement 2, measurement 3, they can do, and you can add those into these columns. And if you look at this one right here, which is a result, and remember, we said we want the part-to-part variation as high as possible, right? As you can see here, it's huge. And the operators or the other variation is very small. And that this is actually telling me that this is a good acceptable gauge or measurement system. Another criteria here, it says the number of distinct categories says 39. That's way greater than the 5 that we talked about. So this is a good example of a good, again, good gauge or study. The quality tools gauge study. Now, after we created that plan, then you need to come in here and select. There are multiple different options to analyze the data. What we want to do is we want to use the Gage R&R study for crossed. And when you do that, again, this is another part where you can go in there, look at the part, the operators, the measurements. In the options section, when you select the crossed, you're going to have to come in here and define what your lower and upper spec limits are. And study variation, by standard, we're using 6. That's the 3 plus minus 3 standard deviation. That gives you 6 standard deviation. And the alpha, to remove the interaction term, we always, again, it's a standard, we use 25%, sorry, 2.5%. So once you do that, click, and that's the result that you're gonna get. So when we look at here, number of distinct categories, again, is 39. And when you look at the total gauge R&R, it's very small, right? So another, sorry, where is that? Percent study variation right here. It's 3.56% as compared to part was 99.94%. As I was saying before, so that's the X-bar and R. So when you look at the same study using the ANOVA, it actually also provides you the interaction effect between the parts and the operators. So what does that mean? Is that if you look at the total variation, it's very small. So again, this one is actually telling us that this is a good, these results are slightly different, but again, it also gives you an additional information about the parts and the operators interaction, and sometimes this could be really high. This usually happens in, believe it or not, in chemical industry where you know how two chemicals alone, right? They're not like doing anything, but when you put them together, there's this interaction, right, effect that you will see. So they're reacting one another. So we do have in some of the processes like that. For example, when you have a press under heat, may not be an issue. The results may be the same, but when you add the humidity, right? So now you may have some electronic components in there that very sensitive to the humidity and heat at the same time. So that's now the interaction between the humidity and the temperature that we have to consider when we're conducting some of these studies.